Okay, all of you have your exams. I graded out of 90. The distribution was very bimodal. I was just drawing this out for Chad. There are 5 people who got A's, 0 who got A minuses, 1 B plus, 2 B's, 0 B minus. What was it? 1 C plus, 1 C, 2 C minuses, nothing in the range of D. And then 5 in the F. It was not the outcome I would like to see. I would like to see these people here up in this range.
I thought there was 18 in the class.
There is one more that is ungraded. You actually counted. Yeah. So I'm not perfectly satisfied with the outcomes, but that is what it is. There's no point trying to hide what the outcome is. So, if you have anything you want to discuss about the test, things that you didn't understand you want to learn, please feel free to come and spend some time with me so we can go over it. Okay, today we're going to look at, the brachistochrone problem first. We're not going to solve this. In fact, we're not going to do any equations about it. But then we're going to use that as a jumping off point to go backward in time to Fermat's version of the brachistochrone problem. So, what is this brachistochrone problem? 2 words. Brachistos means shortest, chronos means time. So the brachistochrone problem is the problem of finding the shortest time. And the famous brachistochrone problem comes from Johann Bernoulli in 1696. He put out a challenge. And he challenged mathematicians to solve a problem that Galileo had solved in 1638. Incorrect. Galileo had made a mistake, and he said that the path that would take the shortest time to go from A to B would be a circular arc. That is, what Galileo had said was, if you have point A here and point B here, the circular arc that goes like this is going to be the fastest way to go from point A to point B, the fastest path. And so Bernoulli said, he had worked it out and said, Galileo was wrong, so he put out this challenge. Now, he put out this challenge in a kind of funny fashion. He had a number of solutions that were submitted, one from Isaac Newton, who did it in 12 hours, another one from his brother, probably pronounce it Jakob or something like that, one from Gottfried Wilhelm von Leibniz, who was his friend, one from Guillaume-François Antoine Marquis de l'Hôpital, famous for L'Hôpital's rule. And Twissaw, feel free to laugh at me as I butcher these names. I'm doing my very best. Of particular note of interest to me is Newton's solution. John comes out, he sat down 12 hours later, he provides his solution. But Bernoulli was good friends with Leibniz, and there's the whole controversy about who invented calculus. And so Bernoulli, when he put out the challenge, he put in some verbiage to tweak Newton. I don't even remember what it was. And so Newton solved it, and with his solution he said, I don't appreciate being pestered by foreigners about mathematical things. So he basically was challenged, he had to do it because the guy had tweaked him. But he put in his statement about, I don't appreciate having to do that. So the solution, and this is from Newton's diagram for the way he solved it, is actually what we call a cycloid. That is, the fastest path to go from point A to point B is to follow a cycloid, which has a mathematical description. And like I said, we're not going to go through and solve this. But you might I think I broke it this year, right? My little track with the carts, and we talked about which track was going to win the race of the two carts going down the track. I must have broke it last year. I broke it at any rate. And the answers people usually give are either the straight line will be the fastest, or the lower one will be faster because it was going faster. It is correct on that case that the lower one is faster because it's going faster even though it's a larger length. But if the path had gone something like this, that would have taken a longer time, right? The cycloid is the path from beginning point to ending point that's going to be the quickest. Okay, so that is the brachistochrone problem, the famous one, not the one we're looking at. So it is important in physics because based on this problem and discussions people had about how they solved it, Euler came up with his English is escaping me. Euler came up with his method of variations. A method of saying, okay, if I minimize this and minimize this, I can get an answer. And that is now heavily used in physics. In your class, you have learned to solve basic dynamics problems, either using forces in Newton's second law or work-energy relations. We use the method called Lagrangian mechanics, which is, and you see Lagrange up there, a method of variations as a third way of solving those problems. Now, Lagrangian mechanics is using actually the energy method, but it's using a variation of the Euler method here, the brachistochrone problem, in order to solve these problems. And all physicists love it because you make a Lagrangian that is your kinetic energy minus your potential energy, and then you just take partial derivative of this is equal to partial derivative of that, solve the equation, and it tells you what's going to happen. It turns out to be really simple. So what is the brachistochrone problem we're going to look at? We have to go back to before Bernoulli's brachistochrone problem, to when Fermat proposed that light going from point A to point B is always going to take the path of shortest time. Well, the meaning of those words, brachistochrone, means that was a brachistochrone problem. That the word just slaughters my tongue. So this was 1662, which if you put things in perspective, was before the problem of Bernoulli, but not by a lot. And so we're going to look at this and we're going to solve what path light will take using Fermat's principle and then compare it to see if that is what really happens. So we're really going to do some mathematical solution to see if Fermat was right. Now this is not Fermat's famous last principle. It's one of the earlier ones. So here's our problem. Now we start off with, being from California, love to go to the beach. I was thinking about how I'm going to teach this last night, and I was like, okay, so you're a lifeguard, and I then looked at, this is the lecture I gave last year, and I had the picture of, you're the lifeguard. And you have a person out there that's in the water drowning. Now, you can run on that sand probably 10 to 15 miles an hour easy. But your swimming is probably in the ballpark of 2 miles an hour. So if you want to get to that person really quickly, what things would go through your head to decide which path is going to get you to that drowning person the fastest?
Probably want to instead minimize your swimming.
Probably want to minimize your swimming because your running is 5 to 7 times faster than your swimming. You really want to minimize that swimming time. So most of us would take that purple path. Well, not exactly that purple path, right? I'm pretty sure what they teach the lifeguard is to run in a straight path, of course in a straight path, why would you take anything else, to the point directly, well,
Are you writing something? Oh, I see.
directly up from the person and then swim perpendicular to the shoreline to get to the person. Because the speed on sand is so much faster than the speed in the water. But we're going to essentially, well, what this illustrates is, of course, you're not going to take the path of shortest distance. Anyone who takes that cyan line is going to spend a lot more time swimming than necessary and slow themselves down. The two extremes would be ridiculous, right? I'm going to run until I'm directly in front of them on the sand, then I'm going to sprint down the sand to the water, and that wouldn't be the wise move. And neither would the one, I'm going to run into the water and swim out until I'm the same distance away from shore and then go. Yeah, those would make no sense. But the one that's best is the one that's shown in purple here. And you notice that the path that I drew is very similar to the one in purple. You just go a little bit farther in the sand for a little bit shorter in the water. Why are the differences so small? Because the difference in speed is so big between sand and water. If you just went slightly slower in the water, you would take a line that's closer to the cyan line. So let's go through and do this calculation. So we have over here a situation where we have medium 1. Let's say this is, let's say this is water. And then you go into medium 2, and let's say this is, I don't know, diamond. It doesn't really matter for our problem what they are. Just you have two different media, and the divider between those two media is this horizontal line. And so we want to find the path that will take the least time to go from what's marked here as point P. I should have gone through and just renamed it. I am going to quickly rename a bunch of things. I didn't think about renaming these when I renamed the indices of refraction. Whoops. Okay, got rid of everything I'm not interested in, and we'll name this from point A to point B. Good? So we want to find the path that takes the least amount of time. So we have drawn a proposed path that goes from A to position that I will call C, and then from C to B. We need to find an equation for the time it's going to take. We're going to minimize the time. We need to find an equation for time. So what kind of equation can I find for the time it's going to take to go from A to B? We want to see if Snell's law is correct. Snell's law is not a time equation. You can't get time from Snell's law directly. More specific, what do you mean? I'll start by writing something that's clearly obvious. The time to go from A to C is equal to the time to go from A to B. Time to go from A to C plus the time to go from C to B. That's clearly obvious, right? How do I find the time to go from A to C? Okay, kinematics is broad. I want the specific. So we know that by definition, speed is equal to the distance over time, right? I'm going to put V equals D over T just for getting the equation out there. So going from A to C, I'm going to have the time is equal to the distance from A to C divided by the speed from A to C. Does that make sense? That's what you said, right, Tori? Okay. What is the distance from A to C? Look at our picture. Look at our variables. We have A, B, and X are our variables. Okay? The distance A to C is the square root. I'm sorry, I keep going lowercase instead of uppercase. Is the square root of A squared plus X squared. To make sure everybody sees that, we have a right triangle with A on one side and X on the other. And so we have that equation for the hypotenuse. What about the speed? Okay. The speed, the index refraction is defined as n is equal to c over v. So if I want to solve that for v, it's just c over n. And so in material 1, it's n1.
Isn't that kind of begging the question, though? Because isn't this whole point that we're deducing what the index of refraction is?
The speed, just like when I was talking about the lifeguard, we could assume the speed is known in the material. We're trying to find a path that's going to be least time.
Right.
And so knowing the speed or knowing n is the same thing. We can assume we're going to know that. What we're looking for is the time it takes to go through from A to B. So putting these together, I have the time to go from A to C is equal to the square root of A squared plus X squared divided by C over N1, or writing that more succinctly, N1 over C times square root of A squared plus X squared. So that's the equation that gives me the time to go from A to C. How about the time to go from C to B?
Square root of d minus x in parentheses squared plus b squared over c divided by
You can't see
Let's see if
the picture anymore? Okay, well, yes, the spacing, I can just barely fit it in there. You have the vertical portion here is b, so that's going to be b squared. And the horizontal portion is d minus x, so plus parentheses d minus x and parentheses squared. So there's the d. The speed, just like before, is going to be speed of light divided by n2. So that gives me the time So there's my time to go from C to B. So what's the total time for this trip? Well, the total time is just going to be where I gave them the common denominator of c. Why? I just want to. So now I have the total time it's going to take. How can we minimize the time? You've all had calculus. Jared says, okay, then it must involve calculus. The derivative. What specifically is that derivative test?
Just the places where it's zero, or where the slope is zero. Minimum, maximum.
Okay. That specific test is the derivative of my variable, or my function, with respect to the variable that can change, evaluated at the critical is equal to 0. But I have to decide, what's my variable that can change in this problem? What is the thing I'm looking for? If the thing that's going to tell me what the path is. It's x. I mean, I'm going to go back to the picture so we can have everyone verify that. I have going from A to B, and x is what's going to really define the path. If x is short, then I'm coming down here and going long in the second one. If x is long, I'm going over here like that. X is what's going to define the path. Because it's going to go in straight lines from A to C, and then from C to B, and x is the position where C is. So we're going to minimize in terms of x. So that means I'm taking the derivative at x, and it's going to be evaluated, and I'm going to put x sub 0 just for the x that gives me the least amount of time. So now I have to take the derivative of that with respect to x. I can factor out the 1 over c. That's actually why I put it all times 1 over c. Help me with the derivatives, everyone. Back row. Be like, spin the bottle. I'll spin this. The person in the back row that it comes closest to pointing to is going to get called on. Closest to pointing to you, Michael.
Oh boy. Well, you can separate the N1 part and the N2 part.
Yep. So Michael is just going to take the derivative of this part.
We're saying N1's a constant, right?
That's correct.
Okay.
Everything except for x is a constant.
And we need to use trainable on the square root part.
Okay, so lead me through.
Well, since square root is like that section to the 1/2,
Mm-hmm.
you can bring down the 1/2 in front of it. And then you have the middle part. Like the same, like the ace, the square root part.
I'm not sure what you mean by middle part.
Oh, sorry. It makes sense in my head, but it doesn't make sense when I say it. Like the a squared plus x squared in parentheses.
Where?
After the 1/2. Or
On the numerator or denominator?
it would be on the bottom.
Okay.
I usually put a negative 1/2.
Okay, so I'm going to put down here.
And then on top there should be a 2x. Since that'd be the derivative of what's on the inside.
Okay, now we forgot the n1, so let's put the n1 out front here. Because, yeah. So he did the chain rule. You have the derivative of a square root. So the derivative of the square root is bring down the 1/2, go from 1/2 to minus 1/2. That's why he was saying he usually just writes raised to the minus 1/2. And then you have times the derivative of the inside. The inside was 2x. And right away, let's go ahead and cancel the 2's. All right. Now, one of the other 2 people on the back table.
I'm just going to spin this again. It's Ann.
It just sounds like, I win. Ann, what you got?
The N2 times 1/2 and then the square root of the bottom. And top. The 2x minus x.
Okay, not quite. Bring down the 2, then you have d minus x, and then you have to do the chain rule again. So we have to do the derivative of the thing inside, right? If it was u squared, the derivative of u squared would have been 2u. But since u is d minus x, then I have to multiply by the derivative inside. What's the derivative of the inside that parentheses? -1. So there we have our derivative. Now, can we simplify this? Absolutely. Once again, we have the 2's canceling. And I can rewrite this as equals 1 over c times n1 times x over the square root of a squared plus x squared minus n2 times d minus x over the square root. So there I've simplified it in the writing. Before I go to the next page, I am going to come up to the top. Well, first I'm going to copy this. Then I'm going to go to the top and I'm going to paste it up there at the top so we can make some substitutions. So I'm just going to paste this right up here. I like the fact that I can do this cut and paste stuff. We have that is equal to 0. Well, if you look at our picture, can you see a substitution for x divided by the square root of a squared plus x squared?
For what now? What are you saying?
This right here.
I can't see what you're pointing
This.
at. A substitution as far as
If you look here, notice this distance right here is x, and this distance here is a squared plus x squared.
yeah.
So I have this divided by that. That would be the sine of this angle here, right? Which is the same as this angle here. So I can make the substitution that this first term is sine of theta 1. With that in mind, the second term, d minus x, is this side right here, and square root of b squared plus d minus x squared is this. So what can I replace this division with? Sine of theta 2. So now I'm out of space on this page. Once again, I'm going to copy the entire thing and just bring it to the next page. Whoops, forgot I had that there. So now what we have is, for time to be minimized or maximized, we have 1 over c times n1 sine theta 1 minus n2 sine theta 2 is equal to 0. Well, very quickly we can say there is no value for c that's going to make this equal to 0, right? So I just multiply by the c across and it disappears. And then just do the quick add n2 sine theta 2 to both sides. And I have n1 sine theta 1 equals n2 sine theta 2, which is Snell's law. Snell's law, I believe, is experimentally determined, although you can also predict it from Huygens' principle. So using calculus and Fermat's principle about how light travels, we get the conclusion of Snell's law, which is not proving Snell's law. It's actually showing that Fermat was correct in positing that light takes the path of least time to go from point A to point B. So you might ask yourself, what was the point of all of this? Well, the point is for us to understand a little bit about this variational method as applied in the brachistochrone problem and how that variational method and Fermat's principle predicts Snell's law. Haben Sie eine Frage? Sorry, I do not speak French. Any questions? All right then, that's it for today.
Good.
Yeah.